gluons interact. The secret of gravity is actually on this transparency, even though the word gravity doesn't appear, as I'll show you in a second. So if you look at the gauge theory vertex, then what you find is there's a kinematic factor here. So that's momenta, and there's also Lorentz indices and so on. And then there's this color factor. The color factor is a group theory, a group theory object, and the color is based on a Lie algebra, and these color factors, being based on a Lie algebra, they obey what's called the Jacobi identity. So this is just a group theory identity. Okay, and that's what color does for a living. So that part's completely standard from the textbooks. Okay, so we're going to take a scattering amplitude at 4 points and just tweak it very slightly. And then something surprising happens. So this is the Feynman diagrams. I take this last Feynman diagram and I assign this Feynman diagram to one of the others, or some, or the piece. If I look in here and I find this color factor, the color factor associated with this diagram in there, I just take that piece, put it in there, multiply by, there's a missing propagator, 1 over S. These are Mandelstam invariants. So I just put in the missing propagator by multiplying and dividing, and I just absorb this in the other diagrams. And as soon as I do that, something remarkable happens. And what happens is the numerator factors, so these are numerators, there's the Feynman propagators, S, T, and U. These numerator factors, they obey exactly the same Jacobi identity. Those minus signs just have to do with the way the diagrams are drawn. It's just some anti-symmetry in there. But the idea is that these numerator factors that depend on, come from the kinematics, have the same algebraic structure as the color. Okay, so that's pretty weird. Where'd that come from? Well, that I'm not going to discuss here. There's actually been a lot of work on that question. But first point you might say is, oh, well, that's very nice, but you're looking at a simple case. It's not going to hold in general, but actually it does hold in general. In fact, I just remembered that I should mention my collaborators, since my collaborator Henrik is right here. So it's Henrik Johansson and John Joseph Frasco. So let's consider the 5-point amplitude. Let's look at the next most complicated one. Then it turns out you can write it in terms of 15 diagrams that only have 3-point vertices, and all these 4-point vertices you absorb appropriately into these other diagrams. Okay, and now the statement is highly non-trivial. It says that there exists a way of rearranging these numerators. So there's some numerators here that you rearrange in some way such that the amplitude is correct. Obviously, you want the correct amplitude. Such that after this rearrangement, the numerators obey exactly the same algebra as the color factors. That's pretty weird. Where'd that come from? In fact, this has been proven explicitly for arbitrary numbers of legs that you can always do this, or actually explicit formulas exist telling you exactly what these numerators are. And there's actually been some progress on unraveling this, which I'm not going to discuss here. And you see, that's pretty weird. Yeah?
If you compare these two relations, on the color side, you can adjust the colors of the incoming particles. On the other hand, on the right-hand side, you can only adjust the polarization.
Right. Well, what will happen is that the only thing this is the algebraic structure. So you should think of this as, you could say, an algebraic constraint. So the specific color, the specific group is not relevant. Only this color algebra, only the Jacobi identity. So it's just a little piece of like the whole, of the color. So that, you could say if I have this color or that color, here's what happens. But never mind. There's a very generic statement for any any gauge group, any color factors. They obey the Jacobi identity. And it says there exists a way such that I can arrange numerators to also have this property. So it's not trivial, okay? Feynman diagrams do not have this property, okay? It's non-trivial to make this happen. Now, okay, so that's, you say, oh, that's very nice, very amusing. There's this very curious relation between coloring and kinematics, and okay, very nice. But what are you going to do with it? Well, here's what we do with it. Gravity. So, see, what happens is once you've done this, once you've made this arrangement, then there's a simple way to get between the gauge theory, so I put QCD here, so it would be all gluon amplitude in QCD at tree level. And this is Einstein gravity, and yes, I do mean Einstein gravity, the real thing. You can go between these two simply by taking the color factor and replacing it with another numerator factor. That's very cool, right? Because this gives you gravity. It's like magic. These numerators, just to reiterate, are in terms of polarization vectors and momenta. They have nothing to do with the gauge group. And the first thing this does, which is actually kind of amusing, it definitely cries out for unification of the sort given by string theory. So, except for one little difference, that we're coming from the bottom. We're just thinking about Einstein-Hilbert-Lagrangian, and we're working with amplitudes, and then we're thinking about the QCD Lagrangian, and we're studying the amplitudes, and we discover that at the detailed dynamical level, the QCD amplitudes are constructed with a certain set of numerators, and it's exactly what you find in Einstein gravity. Okay, so that's something very profound. No doubt these theories belong together. Of course, this doesn't prove string theory. It only says that gravity and gauge theory belong together, very much like it belongs together in string theory. Okay, now you got some harmony. You have two different theories. Look completely different. You would never recognize, not in a million years, that the Einstein-Hilbert-Lagrangian and the Yang-Mills, that's the gauge theory Lagrangian, have this property that they can be related in the scattering amplitudes, that they generate scattering amplitudes where you find this very simple relation between the two theories.
So, is dimension 4 important?
No. Yes, actually, for technical reasons, that's very important because we're going to go to loops. Like I'm here, and we want to use dimensional regularization. So this has nothing to do with d equals 4. If you're looking surprised, you should be surprised. This is a bit of a This is definitely a surprise. This is not expected. Okay, so what are you going to do with this? So to really do something with this, you have to go to loops, where you can have fun at tree level all you want, but certainly if you're trying to understand quantum gravity, you have to go to loops, because the word quantum is h-bars, so it's loops. So it turns out that this idea I just showed you, it generalizes very straightforwardly to loop level. Again, there's a set of numerators for these diagrams. There's a set of color factors. And this is all I'm talking about at the integrand level before you do the integral. So there's some numerator in there, kinematic numerator. And the statement is the following. If you can find a set of numerators such that it satisfies this duality between color and kinematics, by this I mean the duality between color kinematics, that the algebra is the same, then if I want to go between gauge theory and gravity theory, I take the color factor, I replace it with the kinematic numerator. It's like magic. And then the graviton is like two gluons. And this is not the free field theory. This is the fully interacting theory, and we're talking about loop level. So what you can do with this is study, we're going to study the ultraviolet properties. Because now we have a way of getting to extremely high loop orders, the loop orders that no one could imagine we could get to. by doing this mapping between gravity and gauge theory. Now, I'm sure you've heard these statements many times. It gets repeated over and over. I'm sure in Brian Greene's book you could find it multiple times. Einstein's theory of general relativity is incompatible with quantum mechanics. It's kind of a silly statement for many reasons, but never mind. Now, where does that statement come from? Well, there's another statement that's repeated very often, which says all point-like quantum theories of gravity are ultraviolet, divergent, and non-normalizable. Okay, so that's a specific problem. Usually when you hear this statement, they're actually talking about that statement. Now, are these statements true? Where do they come from? Well, it comes from a very simple place. Just some simple power counting. So Newton's constant, there's G Newton. Newton's constant is dimensionful. Carries dimension, so kappa is the expansion parameter. So because Newton's constant is dimensionful, and you compare it to gauge theory, which is a dimensionless coupling constant, then it's just simple dimensional analysis that you have to have some momenta to make up for the dimensions of that. So there have to be extra powers in momenta. It also has to do with the fact that gravitons are spin too. But anyway, let's just focus on the dimensional analysis. So if I put more powers of momentum in my Feynman integral, right, there's more in the numerator, then obviously this gravity integral has a worse behavior compared to the gauge theory integral. So that's kind of trivial. So this is poorly behaved compared to that. Now you can get very sophisticated. You can do supersymmetry, superspace, and hundreds of papers. But at the end of the day, this is the reason. Dimensionful coupling constant. The more loops you have, the worse your problems are. The worse and worse the behavior gets. And this is the origin of the statement. And this statement has been studied in great detail over the years, maybe 1,000 papers. Now, is this statement correct that these theories are poorly behaved? And if you have sharp eyes, you'll notice that there is a flaw in the argument, and it's a flaw which everybody knew about. It's not a hidden flaw, and that's if you're arguing about individual pieces, like an individual diagram, there's a little bit of a problem because it's not a physical quantity. It's only the sum of diagrams that are physical. So you have to worry about cancellations between the diagrams. And this argument does not take that into account. Now, we're going to be looking at some specific theories. We're going to be looking at supergravity theories. N equals 8 supergravity is something we've worked on a lot with Henrik Johansson and John Joseph Carrasco. We like this theory a lot. So it's not a theory that's viable for nature. It has many issues which don't match the real world, but it's just a theoretical toy. So the idea is you increase the supersymmetry. The supersymmetry is the symmetry between the bosons and the fermions, and it's usually extremely helpful for simplifying the theory. The more symmetry you have, the better off you are. So you start with a theory of gravitons, and then you add another 254 states, and you add them just right so that you have a very high degree of symmetry. So it sounds like you're complicating the theory, but in fact you're enormously simplifying. And we're going to be looking at n greater than or equal to 4 supergravity theories. So this is a count of how much supersymmetry. So n equals 4 has half the supersymmetry of n equals 8. So the reason why we like these high supersymmetry theories is more supersymmetry, the better the ultraviolet properties. Maybe some of you have heard the propaganda of supersymmetry, that how it solves ultraviolet problems of various kinds. But anyway, we clearly want more supersymmetry in order to have a fighting chance of trying to find a theory where there's no ultraviolet divergence. And then, of course, high symmetry, technical simplicity. Now, back in the 70s, late 70s and early 80s, these supergravity theories they were seen as the primary means for unifying gravity with the other forces. And here's various quotes. Here's one. So this was Green, Schwartz, and Brink back in '82. They say, if certain patterns that emerge should persist in the higher orders of perturbation theory, then n=8 supergravity in 4 dimensions would have ultraviolet divergences at 3 loops. Okay, and then actually here's one I like a lot. They also said 3 loops, and they said, the final word on these issues may have to await further explicit calculation. Well, that's what we're here to do, right? So, old-fashioned kind of guys. We just want to know what the truth is by doing a calculation. We're going to use newfangled ideas, but exactly that. So, why didn't people check this? So back in the 80s, I say, okay, go do the calculation. If you look at the, actually, if you look at the wording, there's certain patterns, so it's inconclusive, right? So, this is as best as they could do. Based on the patterns they could see, they couldn't find any more cancellations. So then it looked like the fact that Newton's constant is dimensionful causes an ultraviolet divergence. And then the theory would not be consistent as a fundamental theory. That was the logic. Okay, so why didn't people calculate it? And the answer is good luck. It's just not viable. Even with today's modern computers, you try touching one of these things. By 3 loops, even this one diagram can have as many as 10 to the 20th terms in it. 5 loops, 10 to the 31, which, by the way, is more terms than atoms in your average graduate student's brain. So, it doesn't fit in the calculation, can't be done. Now, there's various ways of counting. If you want to debate exactly how to count, fine, but it doesn't matter. Count it any way you want. Calculations to settle this, they seem utterly hopeless. This whole issue seemed destined for the dustbin of undecidable questions. It looks like it diverges. I can't do any more. Time to go on. Okay. Modern methods. So this is the advance. 3 loops today is child's play. It's a very small number of terms. If you want to do n=8 supergravity, 4 loops, very simple as well. 5 loops, well, it's not 10 to the 31, but it's been resisting us. It's on this order of this many terms per diagram. There's about 1,000 diagrams, 1 million terms. It gets a little complicated. Okay. But
sorry, is there a way to understand the factor of 10 increases as a order?
It's simple. It comes from simple counting. A lot of this just has to do with, a lot of this just has to do with the number of possible terms you can write down. The first thing is that we're using, in this counting, I'm using this double copy, so the relation to Yang-Mills. So this count here is really a Yang-Mills count. That's the first thing. And the second thing is the full power of the supersymmetry. We know how to use it. So then, that's funny. That was near that. So the basic idea is basically if you write down all possible terms with certain power counting, this is basically what you get in Yang-Mills theory. But the key point is we're taking supergravity and roughly we're taking the square root of its complexity. So it's now square root complexity. And then on top of it, we have the full power of supersymmetry. So back in 2007, we decided to have a look at this problem because we were quite sure that the 3 loops couldn't be right when they said there's a 3-loop divergence. So we just sat down. We had the unitarity method. We didn't have the duality between color and kinematics at the time, but certainly powerful enough techniques. Sat down, did the calculation. Here's the punchline. It's extremely finite. Now, when you do a calculation like this, and you're at a certain loop order, you know what's going to happen if you say, oh, I found this result at 3 loops. Immediately someone says, oh, that's a very nice calculation, but of course you know you're going to have trouble at 4 loops. And here's a paper from 2009 which specifically said that. It had to do with d = 5. but essentially this is a statement that there's going to be trouble. So, of course, in one of these cases, if someone tells you, well, you know you're going to have trouble, and you're pretty sure you won't have trouble, then of course you make a bet. In fact, that's the bottle of wine, that's an Italian Barello that my friend Kelly Stell put up. And at that point, we had the tools to collect the wine.
How do you know it should be finite before you
You just think a lot about it, but you're never absolutely sure. Well, how about these are all non-trivial, so you're not going to think about doing the calculation unless you're sure you're going to find something interesting. So at least you have a measure of how sure we are that. Okay. So my student at the time, John Joseph Crosco, he was a student, so he wasn't very experienced. So he actually said, "I am not shaving until we finish the calculation." And there he is. This is shortly before we finished. So what is that? 8 months. So it took about 8 months. And this is the photograph shortly after. Now you may notice here he's looking a little stressed out, but he's looking nice and mellow. Okay, what's the result? It's it's finite, very finite. It's not just finite. It's very, very finite. Now, oh yes, that's my competitors, right? So notice the whiteboard. So this is the sitcom Big Bang Theory. The Sheldon is working on this. Okay. Actually, he was at 6 loop, so he was ahead of us. Okay, so of course you do one of these calculations, and you know what's going to happen. That was a very nice calculation you guys did at 5 loops, but of course you're going to have trouble at 5 loops. And at that time, quite a few people got excited by that. There's all sorts of people. Actually, there's Dan Friedman, one of the inventors of supergravity, Michael Green of string theory fame, and a whole bunch of other people. It was Nicholas Bizard who looked at this problem to try to figure out if what we found was something remarkable or something that could be explained by ordinary supergravity understanding. And they had a look at this problem, and what they found was that they could explain all our results, all of them. Every calculation we've done, they explained, and they also said that we'll have trouble starting at 5 loops. Somehow the trouble is always 1 loop beyond where you are. I don't know why, but it's always like that. And by 7 loops, there'll be a valid ultraviolet divergence in D equals 4. So, in fact, based on this, certainly a reasonable person would conclude that n equals 8 supergravity almost certainly diverges at 7 loops in D equals 4. So they didn't prove there's a divergence. They just made symmetry arguments. Now, if you make those same symmetry arguments, you can make various other predictions. One is that n equals 8 supergravity should diverge at 5 loops in D equals 24/5. In fact, Michael Green's paper has D equals 24/5 in it. Don't worry, we're theorists. We can work in any weird dimension we like. That's not a problem. And they also, at least some of the authors, said that n equals 4 supergravity should diverge at 3 loops in D equals 4. N equals 5 supergravity at 4 loops in D equals 4. Now you see an opportunity to make a bet. So the entire community said trouble is going to happen. So I took that as a good opportunity to make a bet. So the bets are at 5 loops in D equals 24/5, does n equals 8 supergravity diverge? At 7 loops in D equals 4, does n equals 8 supergravity diverge? So I have a bet with Kelly Stell on 5 loops. So I'm from California. I put up my California wine. Unfortunately, he's at an English university, so he puts up some English wine. Anyway, he says it should diverge. I also have a 7-loop bet. David Gross, this is with David Gross. I couldn't get him to bet on 24/5 because, it's some weird dimension. He wanted D equals 4. So there's a 7-loop bet. Okay, so unfortunately, n equals 8 supergravity at 5 loops, it's been resisting us. But we're instead decided to have a look at n equals 4 supergravity. And the advantage of n equals 4 supergravity is the interesting things, the places we could show that the consensus was wrong is at 3 loops. It's a much, much more complicated theory because there's less supersymmetry, but then it's a balance. You're at lower loop order, that's easier. You have lower supersymmetry, so it's more complicated, and then it's some balance. But we had this duality between color and kinematics that allows us to build from n equals 4 super Yang mills and ordinary Yang mills with no supersymmetry. We just build n equals 4 supergravity. So it's like magic. Magically gives us n equals 4 supergravity. Now, this magic, it's actually backed up by formalism, this unitarity method. That ensures that the construction is correct, because we don't actually know a theorem that tells us we can do this. Right? It's just a conjecture, but then we have a direct method of checking any construction. And with this, what's an impossible calculation, the 10 to the 20th and beyond, is completely doable. Anyway, there's the punchline. It's finite. All the divergences cancel. Okay. And the only pity is that we didn't bet on this theory. I have to admit that when we got this result, I was thinking I was going to send an email to my friend Kelly. Would you like to bet on this? But then, I don't know. I guess I'm too honest. Anyway, I should have been quicker on changing the bet before I knew the answer. Okay. Now, it turns out that if you go to the next loop order, so that's a very interesting question. Okay, so 3 loops, and sure enough, they said, okay, next loop order, you're going to have trouble. So we had a look at it. It's a recurring story. We had a look at it, and it turns out there is a divergence. So when you first look at this, it doesn't look good. It looks like there'll be a problem. But when we study the divergence in some detail, we could tie it to what's called a quantum anomaly. I mean, there's something very special about this theory. So in fact, the conclusion is exactly the opposite. We found a divergence, but what it shows is that the theories with more supersymmetry, there should be no such divergence. Okay, here's the bottom line. N equals 4 supergravity, it's ultraviolet finite at 3 loops, contrary to what people said it should be, based on standard symmetry. N equals 5 supergravity, it's ultraviolet finite at 4 loops, again contrary to the predictions. And in fact, there's something more specific that we found. So first thing is we proved that in N equals 5 supergravity, the ultraviolet cancellations cannot be, actually I should say N equals, I should say N equals 4 at 3 loops, also N equals 5, also N equals 5 at 4 loops, cannot be made manifest in any Lorentz covariant formalism. And what we called this phenomenon enhanced cancellations. These are not the same types of cancellations that our friends have been talking about. The types of cancellations they talk about and the type they study are exactly the same kind you find in gauge theories. These are not cancellations that occur in gauge theories, and we proved that they're of a different class. And I doubt very much my friends are going to be able to find the standard symmetry explanation. Anyway, they've tried multiple times, and I welcome more attempts to try to get to the bottom of this, to see maybe there is some kind of way of giving a standard explanation. Now, to get the bottle of wine, you have to finish that 5-loop calculation. I think the bottle is mine, just we have to work a lot to actually get it. Okay, so actually what's kind of amusing is this question of whether you can build an ultraviolet finite theory of gravity. It's been given up for dead twice. Once was in the early 80s, and then string theory arose. And the second time was when people looked at the divergences and said, look, there's going to be trouble at 5 loops, and you're going to get a 5-loop divergence. But anyway, we're back in business. There's a very specific phenomenon now to understand these enhanced cancellations. And this is something we're studying now, and I hope that once we understand this, we will be able to construct a proof. Of course, that remains to be seen.